Greetings, aspiring scientists. Welcome to my video today, continuing intermolecular forces, focusing on hydrogen bonding. So it's been a while since I made a video. Sorry about that. I've been busy, but I'm on winter break now. I plan to make a bunch of videos and catch up, cover a lot of things. So let's go to my slides and get into hydrogen bonding. So just to be clear, we are still in the IB syllabus 2.2.8 about intermolecular forces. We have done London forces, London dispersion forces, dipole-dipole, dipole-induced dipole, some of those, and now we're on hydrogen bonding, which is the strongest type, but sort of the most restrictive. It can only be done with very particular compositions or types of bonds in molecules. So hydrogen bonding. Hydrogen often weakly holds its pair of electrons, and electronegative elements are attracted to its concentrated positive charge. So hydrogen usually has one electron, and it will share it with nearby things. If it's sharing it with very electronegative elements, it will essentially become a proton, a positive charged nucleus that attracts other nearby electronegative elements, not only the one that it's covalently bonded to. That's the key. So when they come into contact, a powerful pseudo-covalent bond is formed. It's not a true bond, not a true covalent bond, but it's similar to a covalent bond. And this is the strongest type of intermolecular force. So we will see that things that are able to do hydrogen bonding often have things like higher boiling points, melting points, strength in the solid form. So hydrogen bonding can only occur between hydrogen and several very electronegative elements. These are nitrogen, N, oxygen, O, and fluorine, F. These are the highest electronegativity elements on the periodic table, FON. And these are the things you should be looking for when you're trying to identify if something can do hydrogen bonding. So not only do we need these atoms, these electronegative atoms that can be attracted to a positively charged hydrogen, but we need a specific type of bond. We need an electronegative element, X, bonded to a hydrogen, single sigma covalent bond. And then we also need an acceptor, another electronegative element. I've labeled it Y on this slide, but it is again nitrogen, oxygen, or fluorine. I could have labeled them both as X to show an electronegative element, but I labeled them as X and Y because I want you to know that they don't have to be the same thing. One can be nitrogen, the other can be oxygen, or one can be oxygen, the other fluorine. Just as long as X and Y are one of these electronegative elements, we can have a hydrogen bond. And Z is just anything, doesn't matter at all. Okay, so this is the situation we need. And the reason is because Y needs to be very electronegative with a lone pair. Okay, there must be a lone pair involved in the hydrogen bond. The lone pair is the very negative charge dense region that will be super attracted to the positive hydrogen. So the hydrogen is highly positive, and the lone pair of a nearby electronegative element is strongly attracted to it. Okay, so it's a good idea to draw that one of those lone pairs on Y. You know, Y might have one or two or three lone pairs, but I'm just showing one here to show this is how the bond is really made in hydrogen bonding. So we get a polarized H+, not a full positive charge, but more positive than usual, and a partial negative charge around the lone pair. That forms an electrostatic attraction, fairly strong one. So here's some examples. We could have hydrogen bonding in water, H2O. We have an OH, that's like the XH bond from the previous slide. And then we have an O with a lone pair to accept that H. So you can imagine water could actually form more than one hydrogen bond at the same time. We'll see that in a minute. You could also have ammonia here in the middle. Nitrogen is very electronegative with a lone pair. So if you have a bunch of ammonia, it will hydrogen bond with itself. NH the H becomes positive, then N lone pair donates it to that H. You can also have HF, hydrogen bonding, hydrogen fluoride or hydrofluoric acid. Lone pair donates to H, which is in the HF bond. These are all possible, but these are not the only possibilities. Okay, I was trying to explain this slide, but what I was saying didn't make a lot of sense. Let me try again. So, something that you have to look out for is that some molecules and compounds can participate in hydrogen bonding, even if they couldn't on their own. Things that can't hydrogen bond with themselves can hydrogen bond with other things. Because one of the conditions for hydrogen bonding is you need that XH bond, something like OH, NH, FH. The other condition for something to be a acceptor or a donator of lone pairs is it just has to be one of those electronegative elements, O, F, N, with a lone pair that's not bonded to something else. So here's an example with dimethyl ether, CH3O, CH3. That cannot hydrogen bond with itself. There's no OH bond in that, no XH to start the hydrogen bond. But if you mix this with something like water, water has the OH bond, but dimethyl ether, CH3O, CH3, still has the Y, the electronegative element with some lone pairs to accept that OH bond. So it can hydrogen bond when mixed with water, but not with itself. CH3O, CH3 cannot hydrogen bond with itself. So you have to be on lookout for this kind of thing too. Okay, what else can we say? Water. So you can see water can make hydrogen bonds, more than one, and in fact, water has a ridiculously high boiling point at 100 degrees for such a light compound. Its molecular weight is 18.02. If you look at other things with such light molecular weight, they're very often gases at standard temperature and pressure. But water, even though it's very light, does not have much London forces at all. Still, it remains liquid and boils at 100 degrees Celsius. And I think that's because it can make up to 4 hydrogen bonds per molecule. It can donate 2 H's, and it can accept at 2 lone pair locations on the opposite side of those H's, right? So just like this one in the middle, it can accept on 2 lone pairs, and it can donate 2 hydrogens on the bottom. So these kind of red lightning lines are the hydrogen bonds, and the regular blue lines are the covalent bonds. Tried to make this with Google Gemini. I think it did a pretty good job, although if those little white dots are lone pairs, it's not quite the right number. Okay, what else can we say? So let's consider ice versus liquid water. So the strange property of hydrogen bonding causes ice to be more spread out than water, and this has a lot of consequences. So I think in ice forms a pretty rigid, well-organized crystal structure where hydrogen bonding occurs at 4 positions on each hydrogen. So you can have 1 on each hydrogen place and 1 on each lone pair place. And I've tried to show it here in 2D, but really it's a 3D kind of stacked crystal structure, I think, probably making hexagonal rings like this. And if you go beyond this, I've actually read recently that there's different types of ice crystal structures. There's like ice 1, ice 2, ice 3 that form at different temperatures and pressures. But the one on Earth here I think is ice 1, and it always involves the the waters, H2Os, spreading out more than when they were in the liquid phase. And that means all ice on Earth essentially takes up more space than the water it came from. That means it's less dense, it floats on that water. That's why your ice in your drink floats. That's why icebergs float and don't sink to the bottom of the ocean. But that's hugely important for a lot of things on Earth, such as why Lakes don't freeze at the bottom. They freeze at the top, or wherever they would freeze, the ice floats to the top and creates a kind of insulating barrier, stops the rest of it from freezing. Just one example. So again, comparing that with liquid water on the right, liquid water also has hydrogen bonding, but every water may not have 4 hydrogen bonds at once. Some of them have 1, some have 0, some have 2, some have 3, some have 4, and they're constantly kind of being broken and reformed and partially formed with different strengths, giving it the fluidity of liquid water that we know of. Okay, so the hydrogen bonding in ice, spreading it out, reduces the density that insulates the water underneath and allows large bodies of water to avoid freezing, as I said. So water is quite unique in this way. What else can we say? Okay, compounds that undergo hydrogen bonding have high boiling points, as you would expect. It's harder to pull them apart. High surface tension. This is a hard thing to explain, but it's like when you have little parts of this liquid, do they tend to attract each other strongly and form kind of spherical shapes? You might notice when you spray some water on a plastic or on an oiled surface, you get a bunch of little curled up drops in a spherical shape. If you try the same thing with things that don't hydrogen bond, like, I don't know, gasoline or makeup remover or other stuff, you'll find they just fall flat and create a film of liquid on the surface. They don't sort of curl up into balls and spheres, whereas things with hydrogen bonding do. They have strong forces that pull themselves together. Hydrogen bonds are still about 10 times weaker than true covalent bonds, so even though we're talking about them as if they're this super strong thing, they're not comparable really to real covalent bonds. Hydrogen bonding in water is an important part of Earth's weather, biological systems, and experiments, chemical experiments in industry. It's a very important solvent, as you can imagine, that dissolves things and allows them to mix together and allows collisions and decently fast rates of reaction. So let's do a bit of practice here. Which of the following can form hydrogen bonds with themselves? Methanol, CH3OH, sorry, this has an OH. So, if we just draw that structure quickly, I'm not going to draw the whole 3D dash wedge lines, but for this purpose we can just check if we have the XHY kind of structure. COH. So if we have two of these side by side, I do believe we can have the XHY kind of interaction here. You can have the O with its lone pair from another methanol. Something like that. So yes, methanol can do hydrogen bonding with itself. Fluorine F2, no. There's not even a hydrogen in this, so it can't do hydrogen bonding. I think simple as that. Fluoromethane. Here's a good trick one, because a lot of people would say, yes, this has the electronegative element fluorine, and it has hydrogens. Therefore, we can have the XHY structure. But if you actually draw this, it is not so. So we've got F with its lone pairs. But where would be the hydrogen to bond with this? The hydrogens bonded to carbon are not polarized enough, okay? They are sharing fairly equally with the carbon. Carbon doesn't take enough electron density to make those hydrogens positive. it doesn't have the XHY structure that I showed to indicate hydrogen bonding. So no, CH3F cannot. Okay, number 2, draw a diagram to show hydrogen bonding between two ethanol molecules. Okay, I'm just going to draw some quick skeletal structures to show this. Here's an ethanol, and maybe this will interact with another ethanol nearby. Its lone pair will interact with the hydrogen. Okay, maybe hard to see what's carbon, what's oxygen there, but generally if you have this OH-O shape and interaction, that's showing the hydrogen bond. So then number 3, draw a diagram to show hydrogen bonding between a water molecule and a methanol, CH2O molecule. So methanol usually cannot hydrogen bond with itself. If you try to draw this Lewis structure, the only thing that really works is this. Carbon double bond O, then an H in each of the other positions. So we've got lone pairs, but we've got no OH bonds to fit that XH structure need. But a water molecule can. It has an OH bond, so this can be the donator of hydrogen. And it will do so. So we'll have a hydrogen bond here in between this hydrogen and this lone pair. That should be fine enough to show what the interaction might look like. Let's move on. Here's an important graph, okay? Hydrogen bonding anomalies. So let's try to understand what this graph is. Y-axis is boiling point. So we're seeing the strength of intermolecular forces. And on the bottom, period number. And then in each period, we've got 4 things. So we're just looking at some of the non-metal compounds or non-metal elements bonding with hydrogen. H2S, H2S, H2TE, HCl, HBr, HI, PH3, AS, H3, SBH3. So we're just taking everything on the periodic table and just filling its bonding spots with hydrogen, and seeing if we can see any trends. So if we just look to the right of the circled or the oval section I drew, you can see a pretty clear trend. Everything increases as you go to the next period. So HBr, higher boiling point than HCl. Selenium, H2Se, higher than H2S. And the reason for that, we could just explain it with London forces. As we go to the next period, we have more electrons in that structure, more chance for polarization, instantaneous dipoles, induced dipoles, and the forces get stronger, the boiling point goes up. Okay. That's explainable, and that's probably the main reasons why. But as you go in the opposite direction then, you might expect, as you decrease the period and you go from 2 to 1, those boiling points would be the lowest of all. But actually, they are basically higher than any of the other periods, specifically for group 15, 16, and 17. Not group 14. Okay, group 14 actually does what we expect. That's CH4. It's lower than all the others on its line, SiH4, GeH4, SnH4. So no problem there, it's as we expect, but it's the others, group 15, 16, 17, that contain nitrogen, fluorine, and oxygen. They are higher than anything else in their trend line. It's a massive jump, and we need to be able to explain that. So hydrogen bonding is an explanation for that. These are very, very electronegative elements, NFO. When they bond with hydrogen, they pull its electron density away, but that causes the positive hydrogen to be able to form very strong electrostatic attraction and pseudo bonds with the things around it. Makes the boiling points go way up. Okay, what else can we say? Intermolecular force comparisons. Let's get some real numbers here. So London forces are generally weak. In kilojoules per mole, they are 1 to 10 kilojoule per mole, but there's almost, remember, no limit on this. If you get very big things, it's going to go beyond 10 kilojoule per mole. Think of something like polymers, like, I don't know, PET bottles, plastic. Those have hundreds of thousands of covalent bonds in the molecule, and therefore the molecular weight is high. There's a lot of electrons. As two of those chains get close to each other, it's going to form a very strong attraction, probably greater than 10 kilojoule per mole. Dipole, though, weak to moderate, 3 kilojoule per mole to 25, somewhere in the middle. And hydrogen bonding, moderate to strong, 10 to 40 kilojoule per mole. Okay. So dipole can scale up as well, depending on the strength of the dipole, how much there's an imbalance of charge in the molecule. Hydrogen bonding can sort of scale up. It just depends on how many locations there are for hydrogen bonding. If there's only one, you're going to get maybe numbers like these. If you could have 2 or 3 or 4 between molecules, I think these can get higher as well. Okay, so a summary. London dispersion force, LDF. This is between all molecules and atoms. It's due to instantaneous dipoles and induced dipoles and polarizability. Dipole-induced dipole forces. This is between a polar molecule and non-polar molecule. When a polar molecule induces a dipole in a nearby non-polar molecule. Then we have dipole-dipole forces. This is between polar molecules. Permanent dipoles can form permanent attractions then. Hydrogen bonding. This is between a highly electronegative atoms, FON, lone pair, and a low electron density covalently bonded hydrogen atom. So it's that kind of XHY structure where hydrogen is bonded to one of these very electronegative elements, and then a lone pair comes in and it forms an electrostatic attraction. And generally, there's increasing strength as you go down this chart. Practice. What are the intermolecular forces in the following compounds and mixtures? Butane, CH3, CH2, CH2, CH3. This is nonpolar and no hydrogen bonding or anything. So we can just write LDF, London dispersion forces. Okay, let me just get all the questions here at once. Then we'll answer. So B, ethoxyethane. This is very similar to methoxymethane, CH3OCH3 that I showed on a previous slide. This one just has 2 carbons on each side instead of 1. So this can have LDF, London dispersion forces. And this will be a polar molecule because the oxygen pulls electron density. You can try to draw the vectors. I'm not going to draw them all here, but take my word for it. The oxygen pulls electron density unequally, and this will form a dipole. So we'll just call this dipole forces. But this cannot do hydrogen bonding. There's no OH bonds in this. Carbon tetrafluoride, CF4. This will have London dispersion forces. It will have no dipole. It's not a polar molecule. All the vectors cancel out, even though the bonds are polar. No hydrogen bonding, no hydrogen in this. So just London forces for that. Okay, what else? Ethanamine, CH3, CH2, NH2. LDF, everything has LDF. Dipole-dipole, for sure. This is a polar molecule. The nitrogen-carbon and nitrogen-hydrogen bonds are polarized. And this will have hydrogen bonding. We'll call it HB. So all three types on ethanamine. It's got that NH bond and the N lone pair for hydrogen bonding. E, fluoroethane. You can draw the structure if you need, but I think you'll find this has London dispersion forces, LDF. Dipole-dipole, the polar CF bond. Any hydrogen bonding? No. There's no FH bond. And I know that because fluorine can only form one bond, really. And it's bonded to carbon in this chain. So just London dipole-dipole. Okay, what else? Chloromethane with methane. So these will have LDF. Oops. There will be dipole-dipole between CH3Cl molecules. There will also be dipole-induced dipole between CH3Cl and CH4. But no hydrogen bonding. There's no F, O, or N in either of these. So London, dipole-dipole, dipole-induced we could have. Just to be clear though, methane does not have dipole-dipole with itself. Only London and dipole-induced. Okay, G, water with hydrogen fluoride, H2O and F. So we're going to have London, everything has London, LDF, dipole-dipole, both of these can do dipole-dipole. Hydrogen bonding, yes, for sure. We have OH bonds and HF bonds. So they can hydrogen bond between themselves, molecules of the same type, or they can hydrogen bond between different types. You could have an H2O hydrogen bond with HF. Okay, good things to consider. Moving on, maybe more practice. Determine the intermolecular forces that attract the following molecules together. Propane. Okay, more of the same type of thing. This has only LDF. No dipole. Hydrogen bromide HBr. LDF. And dipole-dipole. But no hydrogen bonding. Hydrogen cyanide. LDF. Dipole-dipole. I think it has a very strong dipole. Hydrogen bonding here. No. There's no NH bond. If you draw this structure, I've drawn it in my videos previously for sure. There's no NH bond in this. So LDF, dipole-dipole only. Ammonia and oxygen gas. LDF. Dipole. Well, this question is asking what attracts the following molecules together. So if we consider what attracts ammonia and oxygen gas, it's not necessarily dipole-dipole, but dipole-induced dipole, because oxygen gas does not have a permanent dipole. So DID, dipole-induced dipole. And I think there can be hydrogen bonding between ammonia and oxygen gas. I just looked this up before I made this video. Couldn't find any clear examples, but in theory and based on the rules we studied, there should be hydrogen bonding possible between ammonia donating through the NH bond onto a lone pair of an oxygen, O2. This should be possible. It is an XHY kind of structure. Okay, ethanal, CH3CHO, just with itself. This will have London dispersion forces. This will have dipole-dipole. Should be polar. But no hydrogen bonding. Ethanal will be this structure. So in this, you have hydrogen bonded to carbons only, no OH bonds. So even though there's lone pairs and there's an oxygen here, cannot hydrogen bond with itself. Okay, 2. State which of the following can form hydrogen bonds with water molecules. Ammonia, yes, definitely. NH3. Propane, if you look at above, propane is CH3, CH2, CH3. There's no electronegative elements in that. Well, no, none of the top 3 very electronegative ones, so this cannot. Ethanoic acid, yes, definitely can. This COOH at the end represents this kind of structure. And so this can both accept or donate hydrogens or lone pairs. So definitely can do hydrogen bonds with water, which means that they will mix very well. Okay, I think that's all I have for today. Yeah, so next time we'll do covalent networks, or giant covalent networks they're sometimes called, and see how they relate to what we studied so far, covalent bonding and intermolecular forces. Hope you learned something. Thanks for listening. I'll make the next video quite soon. And if I don't talk to you again, Merry Christmas, Happy New Year. That's all for today. See ya.